All right, vaporization is up next. We've saved vaporization for the end so that we can truly talk about this phase change from a liquid to a gas, along with heating curves. And so we're going to do a little bit in terms of the physical properties of liquids and gases and that transition between liquid to gas phase, which we know is an endothermic process, right? Heat has to be put into the system in order to overcome the intermolecular forces so that particles can escape out into the gas phase. Notice all of these little shoots are coming out of the gas phase. Sometimes a molecule will go back in to the liquid phase, right? So something a little bit better to understand is that this process is in equilibrium. All right, if we're talking about the liquid going to a gas, that's endothermic. If we're talking about the gas coming back to a liquid, exothermic. But we have talked about the dynamic equilibrium before, and so that's what we're really going to be discussing a little bit more in this video, and also understanding what is occurring in terms of the intermolecular forces. Okay, so high energy molecules at the surface could have enough energy just by the thermal energy around them in the surroundings to overcome the intermolecular forces that hold them together, and they can escape. All right, evaporation happens naturally even with a glass of water sitting on a table. The larger the surface area of that container or that substance, the faster the rate of evaporation. We will talk about the kinetics, or how fast or slow something goes, in chapter 14, next unit. Right now, we just want to know that there is this dynamic equilibrium at the surface of a liquid that allows some particles to escape out into the gas phase. And that is when we call what we call vaporization. Fancy word for boiling. Now, only a small fraction of the molecules in a liquid have enough energy to escape at any given temperature, okay? Now, when we think about let's just do a glass of water. Here's H2O. And let's assume that this is at 25 degrees Celsius. Not every particle has the exact same amount of thermal energy, okay? Technically, this is a probability distribution. There is a lot of molecules at one specific energy, right? The fraction of molecules at this amount of kinetic energy is the average kinetic energy, okay? Now, let's imagine this right here is the minimum kinetic energy needed to escape, needed to go from a liquid to a gas. And so this amount right here of molecules has enough energy. We are getting some water molecules to pop out from the liquid to the gas. Now, if we increased the temperature, if we took that same glass of water, let's pretend it looks the same. If we increase the temperature to, say, 90 degrees Celsius, what happens to our average kinetic energy? It's increasing, right? The average kinetic energy is increasing. Boop, 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 boop. Definitely increase kinetic energy by increasing temperature. But notice how this curve is getting flatter. There's not as high a fraction of molecules at that kinetic energy. There's a more spread out distribution. And notice that there are more molecules that have the ability to escape. All right, so we're going to draw two. Nice. The higher the temperature, the more molecules will have the ability to escape. And so that's what we call the faster rate of evaporation. We call it escape energy simply because we're saying it's escaping the point where intermolecular forces are prevalent in the liquid. So the rate of vaporization increases with temperature, the rate of vaporization increases with surface area, and the rate of vaporization increases with decreasing intermolecular forces strength. So the higher the intermolecular force, let's just draw right out the correlation. That goes with a lower rate of vaporization. It's harder to evaporate a liquid molecule when there is a lot of intermolecular forces. We knew that, but now we're looking at it on a more particulate level. Now, when high energy molecules are lost from the liquid, the average kinetic energy of the leftover is lower. All right, if we're removing those high energy particles from the liquid phase and they're going into the gas, then we are lowering the overall kinetic energy of the liquid. That's why vaporization is an endothermic process. All right, sweating, endothermic, cools us off. Yes. If the energy is not drawn back into the liquid, the temperature will decrease. All right. Vaporization requires the input of energy to overcome the attraction between the molecules. Condensation is the opposite of vaporization. Some molecules of the vapor will lose their energy through molecular collisions, bumping into a lid, bumping into the walls of the container, and they'll start to condense back down. If you've ever boiled water on a stove and put a lid on it, you see that the molecules then can't fully escape. They bump into the lid and then they condense as little water particles back on the top. It's when you take off the lid that the water can actually, or the vapor can actually escape. So we can think about this as a real life application. Just boil some water, have some spaghetti tonight, okay? Some particles may stick and gather together to form droplets on the surroundings. So this is truly an equilibrium idea where some vapor molecules are escaping, but then some of them also condense back down. Vaporization and condensation are opposite processes. Again, open container, the vapor molecules generally can spread out faster, and so they can leave instead of condense. The net result is the rate of vaporization is greater than that of condensation. So the liquid will evaporate over time and it will get lower and lower and lower of its volume. However, if it's in a closed container, you put a little lid on that pot of boiling water, the vapor will not be allowed to spread out indefinitely. And so the net result of that closed container is that at some time, the rates of vaporization and condensation will be equal, right? You get some molecules to boil and then they'll collect on the lid and then they'll condense. The weaker the intermolecular forces of attraction, the less energy the molecules will need to vaporize. So it's easier to boil things when they are not held together strongly in the liquid phase. All right, liquids that evaporate easily are called volatile. Gasoline, because all that gasoline has in it is London dispersion forces. And fingernail polish remover, because that's acetone, we've talked about that before, dipole-dipole interactions there. Those are all volatile liquids. They're easily vaporized, all right? When we think about liquids that are not easily vaporized, those are non-volatile. This would be motor oil. Motor oil is a combination of a bunch of things. However, it has more of the idea of hydrogen bonding. And depending on what your proprietary brand is, ion dipole forces. And those are extremely difficult to get to boil and to become vapor. So non-volatile. Heat of vaporization. A heat of vaporization, we're back to enthalpy. Yeah. It's also called the enthalpy of vaporization. It's abbreviated delta H VAP. Beautiful. Delta H VAP is the energy required to vaporize 1 mole of a liquid. It is usually in kilojoules per mole. And we can use it the same way that we've used other delta H's before. It's specifically geared, though, to a liquid to gas delta H. Awesome. So we have been using delta H when we talked about this transition being endothermic, being a positive value for the delta H. We now just call it specifically a delta H of vaporization, or delta H VAP. It is always endothermic and it is somewhat temperature dependent, okay? So depending on what is around the molecule, what thermal energies you're at, delta H VAP will be temperature dependent. Delta H of condensation is the opposite of delta H of vaporization, okay? Going backwards from a gas back to a liquid is the delta H of condensation. It will always be the same magnitude, just opposite sign. Delta H of condensation is an exothermic process, so it would be the negative of the delta H of vaporization. Got some delta H's there so that you can see at boiling point versus at 25 degrees Celsius, we do see a difference here in the delta H of vaporization. That is because at boiling point, the thermal energy and the kinetic energy of all of the molecules of these different liquids are already at the right temperature, all right? If you think about dropping that down to 25 degrees Celsius, the delta H of vaporization is a little bit higher. And that's because we not only have to do the process of going from a liquid to a gas, but we also have to bring the thermal energy up to the boiling temperature. Dynamic equilibrium, just explained a little bit again. In a closed container, once the rates of vaporization and condensation are equal, the total amount of vapor and liquid will not change. Evaporation and condensation are occurring, but because they are opposite processes, there's no net gain or loss of either the vapor or the liquid. So the dynamic equilibrium exists when we still have the processes, but then overall net change of liquid and vapor is zero. And that's because as one goes up to be a liquid, the other one is going back down when one goes up to be a gas, the other one is going back down to be a liquid. Okay, so the overall change is zero. There's a lot of dynamic equilibriums that exist out in nature. One specifically is the process of ozone reaction in the higher troposphere and stratosphere. So when we're looking at ozone in our atmosphere, ozone does fluctuate in between O3 and oxygen gas, O2. In a special reaction, it's ozone depletion that we're worried about. When we don't have the dynamic equilibrium of the flux between ozone and oxygen gas, we can actually get the ozone depletion reaction to occur more rapidly. And that's human problems, right? We have released molecules into the atmosphere that make the depletion of ozone more rapid than the formation of ozone. So lots of dynamic equilibriums, a very important type of topic. We will do a lot more with equilibrium at the very end of the semester as well in chapter 15 and 16. One more type of physical property that we are going to talk about is vapor pressure. It's the pressure exerted by a vapor when it's in the dynamic equilibrium with its liquid. Vapor pressure is going to, again, correlate to attractive forces, but the weaker the attractive forces between molecules, the more molecules will be in the vapor phase, right? So this one is opposite. The weaker the attractive forces, the higher the vapor pressure, because again, the weaker attractive forces in the liquid, right, means that the liquid is not holding on to itself. So more molecules will be in the vapor, and so higher vapor pressure. This is really important to know in the vapor or the gas phase, right? The higher the vapor pressure correlates with a more volatile liquid as well. So changing the equilibrium, we can change a dynamic equilibrium. Think about a piston, okay? So a piston is a constant volume, but we do have the ability to expand or contract, right? Or compress. So in a piston, we have this arm that can move up or down depending on what we want, but when it's set, it is a fixed volume. So that's nice to have that kind of a setup. So in this specific volume right here, we have a dynamic equilibrium. If we were to increase the volume, right, more evaporation would take place, more vaporization, because we are trying to restore the vapor pressure. And if we increase the volume, we've given the vapor more room, and more volume to spread out, and so the vapor pressure decreases. But the rate of vaporization then would increase so that we can establish vapor pressure again. If we were to compress this dynamic equilibrium, we would push down on the vapor that is existing at the top of the liquid, and therefore the vapor pressure would increase, causing the rate of condensation to increase so that we reestablish that dynamic equilibrium, reestablish the vapor pressure. Now, vapor pressure versus temperature charts are really important to be able to look at. We will look at these charts a lot when we start dealing with our phase diagrams. Now, increasing the temperature typically increases the number of molecules that can escape the liquid. And so the net result is that as temperature increases, vapor pressure increases. Small changes in the temperature can make big changes in vapor pressure depending on what molecule you're looking at. Diethyl ether is again that dipole-dipole molecule where we have an oxygen sandwiched in between carbon groups. These happen to be 4 carbon groups, right? All that you would need to be able to understand is that this one, I would tell you, is dipole-dipole. Ethyl alcohol, also called ethanol, is the molecule with the actual OH hydrogen bonding idea. Again, you should note hydrogen bonding there. So we see that the change or that green line is quite different than the yellow orangey line. It's in a totally different spot. Its temperature of boiling is very, very different. And then we see water at the very end here, H2O. Again, hydrogen bonding, just a little bit different. Ethylene glycol is super interesting. Ethylene glycol usually is used in antifreeze. And the reason for that and the idea of ethylene glycol called antifreeze is because it actually has 2 areas of hydrogen bonding. It's a chain with 2 OH groups there. And so it has more hydrogen bonding than water does. And so it has an even higher boiling point and an even higher melting point. That's why it's called antifreeze, and it's used a lot in cars because if we used water, just water in cars, in areas and states where snow occurs for many, many days, the water would itself freeze and the car would not be able to run. So we use antifreeze in cars specifically so that we would prevent any freezing and inoperability of a car. Now, the boiling point of a liquid is the temperature at which the liquid reaches a point where its vapor pressure is the same as the external pressure around it. So our external pressure, we can start to think about if we're at in an open container, normal everyday 1 atm, right? And so the vapor pressure equal to that external pressure is the specific boiling phenomena that we see. And so that temperature is what we have determined as called boiling point. Normal boiling point is when we are at 1 atm. If you go up into the mountains, if you live in Colorado, up in the mountains, or if you're camping, I camp a lot with my family because, you know, it's cheap and my son eats a whole heck of a lot, so I spend more money on food. If we go up into the higher mountains where the air pressure, the external pressure is lower, boiling is easier, but it happens at a lower temperature because the temperature where the vapor pressure is equal to the external pressure is a lot sooner. It's not 1 atm, it's like 0.8 atm. And so that can change the boiling point. Normal boiling point, when we slap on the word normal in front of it, that means at 1 atm. I really like this chart because, you know, I'm just all about hiking and mountainy climbing things now. I know you're like, Lauren, really? When you think about sea level, right? Elevation close to 0, 20 feet, not that big of a deal. Approximate air pressure, 1 atm. You go up to Mount Whitney, which is not too far from me. I have not climbed Mount Whitney before, but it is a place where I have camped by it. It's in Lone Pine, California. It is the highest mountain peak in the United States, the 48 states, right? Look at that atmospheric pressure. It's very difficult when you climb up Mount Whitney. You have to take things a little bit slow. So I've heard. I know people that climbed it, but I have not myself, because the air pressure is so low, right? So the amount of oxygen that you're getting. But look, water will boil at 87 degrees Celsius. Water boils easier, lower temperature than normal boiling point, but that means you have to cook your food longer. If you go up to Mount Everest, highest mountain peak on Earth, Mount Everest in Tibet is approximate air pressure of 0.32. Very dangerous to climb Mount Everest if you do not have the right gear. You need oxygen tanks. You need all sorts of assistance with that. You're going to take a long time to make that spaghetti. Just saying. Heating curves. Let's talk about some heating curves. As you heat a liquid, its temperature increases, right? Until it reaches the point of boiling. So we can use calorimetry. Ooh, calorimetry. Remember this guy? Heat is equal to the mass times the specific heat times the change of temperature. That we can use for this process when we think about heating a liquid, all right? But once we reach that point of boiling, we cannot use calorimetry anymore, because once the temperature reaches the boiling point, heat is going into actually converting and doing the liquid to gas transition, which is the delta H of vaporization, all right? That delta H of vaporization will not change the temperature of the state. It will actually be utilizing the energy to convert from the liquid to the gas. It will be getting to overcome the intermolecular forces from the liquid to the gas. Once we get into the gas phase, again, we start to see that trend again going linearly up. We can use calorimetry again. Specific heat is different for gases as it is liquids, so you might have to change that specific heat. But again, we can look at this overall heat added for a phase change and calorimetry experiment, which is really, really exciting. We can also use a heating curve for melting as well. Melting specifically, we can also use a heating curve for melting. Melting specifically going from the solid to the liquid is also an endothermic process. Delta H fusion is usually what it's called. Again, that is an endothermic process, just like our boiling was, all right? Again, we can see calorimetry can be used if we need to heat up a solid, right? So there's the calorimetry part. But once we get to the actual melting, right, the heat added is used to convert from the solid to the liquid. We're not overcoming intermolecular forces, but we are spreading out the molecules. Solids are very densely packed. We do have to spread them out and increase the distance between the intermolecular forces. And then we can go back to heating the liquid, all right? Any of our slopes here, we can use calorimetry. Any of our flat lines or our plateaus are phase changes. So we would have to use our delta H's. When high energy molecules are lost from the solid, again, the average kinetic energy is lowered, which is why melting is an endothermic process. And especially in this setup with heating curves, we are an open system, so we are trying to add energy in order to melt, okay? Melting requires the input of energy to overcome the attractions among molecules. We're not eliminating all of the intermolecular forces, but we are looking at the ability of the molecules to spread out. Heat of fusion, this is sometimes called the enthalpy of fusion, delta H fuzz or fuse. This is the amount of energy required to melt 1 mole of one solid. So again, looking at solid to liquid, that delta H is called fusion. The opposite, going from a liquid to a solid, is called delta H of crystallization. All right, again, they're opposite in sign, but identical in magnitude. Typically, what's really important is that typical heats of fusion, delta H fusion, are a lot lower than delta H's of vaporization, right? Looking at the blue here, let's color code for a minute. Looking at the blue here, this is going from a solid to a liquid. That's the delta H there. And if we look at the pink, that's going from the liquid to the gas. Why? Well, think about what are we trying to change here? Solids to liquids, we're spreading things out a little bit. Liquids to gases, we're overcoming all of the intermolecular forces. Liquid to gas, boiling, or delta H of vaporization will always be bigger than delta H of fusion because overcoming intermolecular forces occurs in vaporization, in boiling. That does not occur in melting. Melting is a lot easier to do than boiling.